Okay, so we're going to look at non-homogeneous second-order linear ODEs with constant coefficients. That means that it kind of looks like this, and you can get characteristic equations and all this kind of stuff. Now, in the past, we've looked at this stuff where it was equal to 0. That would make it homogeneous. But now we're going to look at it when it's not 0, so it's non-homogeneous. Now, the stuff that we're talking about, a lot of it's going to go ahead and apply to things with non-constant coefficients, so functional coefficients, so just general linear stuff. But in this particular case, just to make things kind of easy to get used to, we're just going to do the constant coefficient stuff. So basically the idea is this. Let's say I have a solution. Say that y1 and y2 solve the homogeneous version. So say it solves this, blah, 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 0. And in fact, I'm going to go ahead and solve this in general so that you believe me. So let me actually fix this. So we'll say that those two solve, blah and blah, solve y double prime plus px. I know I said constant coefficient, but it's going to be fine. You're going to make it. And this way we don't have to do it later because you'll be like, oh yeah, I remember we did that. So anyway, there. Oh, but it equals 0 because it solves the homogeneous version. Now, I'm going to state, I hereby assert, or whatever, because I don't have to hereby assert because it's the way it is, that if you can find any solution at all to the full equation, to the full problem, so to the non-homogeneous version. So if you can find any solution at all to the non-homogeneous version, then we call that the particular. So we call that the particular. YP. Then the full solution is y is equal to y particular plus a linear combination of the two homogeneous solutions. Okay? Ish? Kind of? All right, well, let me prove it, because might as well. So if I have this, and clearly y prime is this prime plus this. It's not a very crazy prime. Oh, I meant to do y2. Like this, and then y double prime is just the same things double prime because they just have constants, and this is kind of a boring little thing to write, but we'll write it anyway. So I said that y double prime, which was this guy, synapse hypothalamus. So we got this. So that's y double prime plus p of x, which is this thing, times, I'm sorry, not p of x, which is this thing, but p of x times y prime, which is this thing, y particular plus c1, y1 dupe plus c2, y2 dupe, like this, and then I'm going to be writing off the page. So that's this plus q of x times all the normal stuff, and I'll move it in a second. There's a bug on my floor and my kitty is eating it. Yucky. Yucky. So this green thing here is this green thing here that you can't see. View, out. So I'm saying that I'm going to posit that that is equal to, not 0, but it's equal to f of x. Now, this probably isn't too hard to see, because basically what happens is if I pull off this term, and this term, well, I guess by the time I multiply everything out, I can rearrange stuff to where I have yp double prime plus yp prime plus q yp, and then I'm going to c1 y1 double prime plus px y1 prime plus qx y2 prime, or y1 regular, and then c2 and then again, the same stuff just with 2's. y2 double prime. This is a lot of stuff to write because it's a proofish thing. It's not really a proof, it's just showing that you shouldn't be shocked by these results. So, zoom out again. So I've got this giant thing. Now, because y1 is a homogeneous solution, then that means that it automatically has to equal 0 because by definition, it equals 0 because it's homogeneous. This is also a homogeneous solution, so it equals 0. This is a particular solution, and we know that that equals f of x because we found one that equals f of x. So basically, the point of this is that by combining them like we did up here, is we're able to show all of the potential solutions and all the linear combinations that amount to the solution. You know, we're able to account for all the solutions that particular differential equation could possibly have. We found the 0 ones and we found the non-zero ones, and when we combine them all, then we basically covered all our bases. So that's pretty much a whole lot of what we're going to do is stuff like that. Now, one more little thing that's kind of unrelated but kind of also related is that I'm going to zoom back in. Right. Woohoo! Right. So another thing that we have, and this is kind of something that can help us. So say we have y double prime plus px, y prime plus q, x, y equals some f1. And I have that y double prime plus px. And so basically, what if I have two problems that have the same thing on the left, but have something different on the right? So let's say that I have a particular solution for this one. So this one solves this guy. And y particular 2 solves this guy. There's a theorem called superposition. And the theorem of superposition says that if yp1 solves the first one and yp2 solves the second one, then yp, which equals yp, basically I can add them together and get a solution for the for this version. And this really shouldn't come as a shock at all, because the same thing's going to happen as if I do a double derivative of this guy and plug him in. So that would just look like this. It would look like, I'm just going to call it y1 and y2 so I don't have so many of these. y1 double prime, y2 double prime plus p, y1 prime, y2 prime plus q, y1, y2. Does that equal f1 plus f2? And of course it does, because all I have to do is rearrange it. So basically what I'm trying to say is there's a lot of like little theorems and stuff that seem kind of arbitrary, but I mean it's really just a question of combining like terms, and it's just really not shocking at all. So does that equal that? And the answer is of course, because this by definition is the solution to f1 of x, and this by definition is a solution of f2 of x. So basically the idea is, so remember one of the first things we said is that if you can find any solution to a non-homogeneous version, well that's kind of cool. Because say you have something really complicated, like say this one is a whole bunch of sines and cosines, and this one is a whole bunch of logs and e's, you can solve the one with the sines and cosines like a little bit more carefully, and then you can solve the one with the logs and the e's, and then you can combine the two of them, and that'll be the full particular solution. It's basically a way to reduce some of the complexity of the problems before you approach it. We also use this a lot in circuits when we turn independent sources off to make kind of simplify circuits. But it's the same kind of thing, is that you can just address one part, just address the other part, and then add them together. So this is a really cool trick. So let me just kind of show you how this works. Okay, so let's look at this example here. Say I have that y double prime plus y is equal to 1. Now, the first step, whenever you're solving something like this, I'm also going to give you some initial conditions. Y at 0 is 2, y prime at 0 is 7. So our first step is always going to be to find the homogeneous solutions. Why? Because we're all about partial credit. And partial credit is like, oh, look, at least you kind of knew something about this material. So we want to solve that we have y double prime plus y is equal to 0. Okay. Homogeneous. All right, so I can pull, since the constant coefficient thingy, I can pull that off to be r squared plus 1 equals 0. So r squared is equal to -1. So wait, is that right? Yes. So r is equal to plus or minus I. And I'm going to go ahead and say 0 plus or minus I because we know that the general form for this is to say y homogeneous is e to the 0, because that's the 0, and then cosine, C1, cosine of 1x, because there's a 1 coefficient there, so cosine of x, and then C2, sine of x. Okay, so I'm just going to go ahead and get rid of that because we know that's a 1, so I just have that the y homogeneous is equal to C1 cosine x plus C2 sine x. All right, now the second step is to find a particular solution. Any particular solution, it doesn't matter what it is. As long as it's not what we just found, it needs to meet, well, because what we just found isn't a solution, because that was a solution of homogeneous. So we just need to find any particular solution. Now, I'm going to go out on a limb, and because I know the answer, I'm going to guess, sorry, that's not supposed to be an H, I'm going to guess a particular solution is just 1, just the number 1. No function, no nothing, just 1. So let's check, make sure we're right. So, since it's y particular is 1, that means that y particular prime is 0, and y particular double prime is still 0. So if I plug that in for that, I've got 0 plus y1 is 1. And I want to know, does that equal 1? Of course it does, okay? So I have a particular solution of 1. So that means my full solution is the particular solution plus C1 cosine x plus C2 sine of x. Now this is really important. You always want to apply your initial conditions after you've got your full solution. Otherwise, if you try to, so what some people will do is they'll try to apply the initial conditions here, which really doesn't make any sense because that's not your entire answer. You really have to wait until you have the full solution to apply your initial conditions. And because the second order ODE, we're usually going to need the derivative to apply the second initial condition. So we've got minus C1 sine x plus C2 cosine x. And my initial condition said that y at 0 was equal to 2. So that's 1 plus cosine of 0 is 1. Sine of 0 is 0. C1 is equal to 1. And y prime at 0 was equal to 7. So that's negative, well, it's 0. Sine of 0 is 0. C2, 7 is C2. So my full solution is y is equal to 1 plus cosine x plus 7 sine x. Okay? Great. Now, 2 questions probably in your head. 1, how did you know how to guess 1? Well, because I'm kind of a genius. And 2, what if you hadn't guessed 1? What if you'd guessed something else? Is there another particular solution you could have found? You're like, I wasn't going to ask that. No, you totally were. And the answer is yes. So you can really, so that's why we call it a particular solution, is because any particular solution works. And I'll show you why. So remember we had y double prime plus y is equal to 1. Now I posit that in addition to the value 1, I could have said 1 plus cosine x. Now if I put in y prime, that would be 0 minus sine x. And then if I did y particular double prime, that would be minus cosine x. So if I plug in a y double prime here, so I'd have minus cosine x plus y, which is this. Does that equal 1? Most definitely it does. Boom, boom. 1 equals 1. We're good to go. So whenever I would make my full solution, I would do my particular solution plus my 2 homogeneous solutions, cosine x plus sine x. Now what's going to happen here? Really the easiest way to say it is just to say that I would have 1 plus c1 cosine x, c2 sine x. So 1 plus a constant is still just an arbitrary constant. So I could just say 1 plus some other different kind of c1 cosine x plus c2. So I end up with the exact same thing. I could have had this be a combination of sines and cosines. So basically the idea is a particular solution doesn't have to be the same one someone else comes with, but ultimately what's going to happen is you're going to end up with the exact same thing even before you solve for your initial conditions. So that's pretty cool. Now the second question was, how did I know how to guess 1 in the first place? All right, that's a little bit trickier, and we're definitely going to do a whole lot more of this, but the basic idea is if I'm looking at this, I'm not really sure, but this is a constant right here. Well, I mean, I'm sure that it's a constant, but I'm not really sure what the solution's going to be, but I know that's going to be a constant. So because this is a constant, I'm going to guess that the answer, the particular answer, is also going to be in a form of the constant. Now, maybe I didn't know what that constant was. All right, so I'm going to guess a general constant, a generic constant, and then I have this, and I can plug it in. So I can plug in 0 for y double prime. So I've got 0 plus y, which was a. And I know that that has to be equal to 1. Well, there we go. That tells me that a equals 1, and I've actually got a good solution. This would work for other things as well. If I had y double prime plus y is equal to x plus 2. I could guess that I'm going to probably have a solution in the form ax plus b. It's probably going to look something like this because whenever all is said and done, I'm going to have an x, I'm going to have a constant. So this seems like as good a guess as any. If I do this, all right, then I've got 0 here, and then I have y here. That needs to equal x plus 2. Now, is it going to? Well, sure, it would if a was equal to 1 and b was equal to 2. Is it always going to be this easy? No, it's just accidentally working out this way. So if I plug those in, I will, in fact, get the right answer. So let me show you where it's not going to be maybe as pretty. Say I had y double prime plus y. We'll call it, instead of y prime, let's do like 2y prime plus 3y or something like that. And we'll call it x plus 2 again, just to make it easy. So again, I'm going to guess yp is equal to ax plus b. So I've got 0 here plus 2y, and I'll go ahead and write these. Yp prime is a, and yp double prime is 0. So there's my 0. I've got 2y prime. Y prime is a. And then I have 3y, ax plus b. And that has to equal x plus 2. So then I can go in here and I can say, okay, so I've got 2a plus 3ax plus 3b has to equal x plus 2, 3ax plus 2a, 3b, x plus 2. So I've got 3a is equal to 1, 2a plus 3b is equal to 2. This is actually called the method of undetermined coefficients. I think so we're going to do a whole lot more of this later. This is more just like a little sneak preview. So whenever you get to it later, you can be like, I know what we're doing. So whatever this is, 2/3, and this is equal to 6/3, 3b, 4/3, and b is 4/9. So basically saying that my particular solution for that one would be in the term 1/3 x plus 4/9, and that would be a particular solution. Well, how do I know it is? Well, I basically just proved that it had to be, but if you really wanted to do this again, I mean, you could go through the process of doing the y prime of 1/3, y double prime is 0, you plug them in, you had, I already forgot what the problem was. It was, the coefficients were 2 and 3. 1, 2, and 3, so it was 1, 2, and 3. And let's go see what that is. 2/3 plus x plus 12/9. Did I miss a number? Or am I just not good at math? That's probably it. Oh, 12/9, I know what I did. Well, 12/9 is totally valid, but I meant to say 4/3. That equals x plus 6/3, which is 2. And that's exactly what I thought I was going to get. So you can do all kinds of crazy with this and be in pretty good shape. So basically your strategy is going to be for all these kinds of problems, and pretty much a lot of stuff like this, not just this in particular. Find a homogeneous solution. Find a particular, find all your homogeneous solutions, and since we're in second order, there's going to be 2. Find any particular solution at all, and then combine your particular with your homogeneous, and then solve for your initial conditions once you have your full solution. So you want to make sure you do, I mean, it doesn't really matter if you switch the order of 1 and 2, but you definitely want this to be, I guess I should have put step 3, like right here, and then you'll be in excellent shape.